coming. It's only now that most of them are joining. So we'll wait for another 3 more minutes and then kick off with today's session. So all of you who are here right now, please make sure that you attend these few more sessions, because these are our 5 last session of this workshop for astrophysics. We've come a long way, and this is the final few sessions we'll be having. If I'm not wrong, we'll have 5 more sessions. So this is the 5th last session we have, and yeah, so at the end of these 5 sessions is when we'll be discussing about our final project, and that project is more of a data analysis and more what do you say, more uh, hands-on intended project. So this could well add on to your you know profile if you'd like to proceed further in the same branch or field. So it's really important that you look into the aspects of these project if you're trying to pursue something of this line. So yeah, again, once again, this is we have only 5 more sessions, so please make sure that you attend the rest of the 5 sessions that we are going to have. Anyway, we will wait for a couple of minutes more just so that everyone joins, and we'll start. Anyway, once again, um, welcome to the session, everyone. All right, so we have 8 participants now. All right, I believe Ripple, you're new to the session.
Yes.
Yes. Could you please introduce yourself? Ripple, am I audible? All right. Akanksha? Akanksha?
Yes.
Yes, I see that you're Sure, Ripple. Yeah, thank you. Sorry, Akanksha. Yeah, I see that you're new to the session. Could you please introduce yourself?
Yeah, hello, I'm Akanksha Shikre, and I've done my bachelor's and master's in biomedical engineering. Yeah, and it's been a month since I've joined this internship. Yeah, looking forward to it.
All right. So, what brings you to astrophysics sessions?
I was just curious about this topic, so wanted to
All
learn
right.
more about it.
Okay. So, we have completed around 25 sessions of astrophysics already, wherein we have discussed about various aspects about the birth of the universe and various celestial bodies like exoplanets, symbiotic binary stars, stars in general, black holes, different phenomena that happen, all of that. So we are the last few sessions of our workshop. So we are on the analysis part of it, data collection, and some data generation and analysis. So hope you can follow at this point. And anyway, hope you have fun.
Yeah,
Thanks
but
for
will
joining
I
our
get any
culture.
recordings maybe then?
Yes, yes, you will definitely. Can you please contact the coordinator, Mruganka?
Yeah, okay, sure.
Yeah, he handles the recordings. He should be able to give you a drive, a Google Drive of all the recordings. Yes.
Yeah, okay, thank you.
All right. And Ripple, could you please introduce yourself?
Hello.
Hi, Ripple. Yes.
Hello. Good evening, ma'am. My name is Ripul Sharma. And I'm from Himachal Pradesh, and I'm in 11th grade.
Oh, wow. Okay. All right. So we've got another buddy from school. That's nice. So what brings you to astrophysics?
I'm just interested.
All right. Cool. Cool. All right. Okay. So again, as I mentioned, we have crossed the major part of the workshop by now. And we'll be looking into some data analysis and some hands-on projects for the rest of the 5 sessions that we have for this workshop, for this course. Anyway, so have fun here, and we'll step into our today's session. So today's session for everyone is about the three major projects that um, I have done. So I can tell you the various challenges and various things I've faced through the project. So this is to get you familiarized with the kind of projects that are out there. There are way more projects that are available. So, out of the three projects that I'll be discussing and briefing you all in today's session, uh, one specific project will be the kind of project that you'll be doing for your major project that is coming up for the end of this course. Right. So, I'll quickly get into it. Please give me a moment. I'm just sharing my screen.
এই চেয়ারটা হ্যাঁ ওকে 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 আমি তো ওটাতে বসি ঠিক আছে থাক ওখানে থাক ওখানে থাক হুম ওই ধুলোবালি পা ফা দিয়ে দিয়েছে তো আর বসতে পারি না ওটাতে
Hope my screen is visible now. All right, thank you. So for the convenience of sharing, I'm just switching off my video for now. Anyway, so this was a project that was handled during an exchange program that I had done um, in a university in France. So we were part of uh, an observatory called La Boutière in Paris, in the outskirts of Paris. So all the data that you see here would be based on the winter sky that is available under the European coordinates. So, okay, let's get into it. Cool. So, I'll be taking you through the depth of details of this project so that you have um, what do you say, a live idea about what happened. So this was my project supervisor. She is a lecturer of physics in the university called IPSA, and she is also the scientific coordinator of IPSA Vega Astronomy Association, and she was a student lab supervisor as well. Right now, she's the president of the association, and so she is has written a lot of journals and articles. You can find her articles in a lot of places wherein you can refer for various research purposes. We'll get into that as well. So this was back when I was doing my BTech. Yeah. So there were three major projects, and first project was called the Exo Clock, which, as the name suggests, is to deal with exoplanets, and we'll be looking into various transit photometry of exoplanets, and we'll be recording them, and we'll be doing some data analysis and we'll try to pull in some data from the kind of light curves that we receive or we generate based on the observations we had. And the second project is HOYS, or HOYS, which is an abbreviation for Hunting Outbursting Young Stars. And the third project was symbiotic stars, or you can rather call it symbiotic binary stars. As the name suggests, and also as we have already discussed about symbiotic stars, it's about a pair of stars that exist together. In most cases, it would be a red supergiant and a white dwarf, or red giant and a white dwarf. So the main idea of this existence of these kind of binary stars would be a red supergiant, as you all know, is very cold in nature. So when we associate it to the color coordination in astronomy, we generally take red as a cold color and blue as a hot color, right? So red giants or red supergiants are extremely big in size but very cold. Okay. On the other hand, white dwarfs would be extremely hot, but as you can see from the name, they are dwarf, as in they are very small in size. So these are the coexistence of symbiotic binary stars. So we will be analyzing, and we'll be looking at various photometry and spectrometry of symbiotic stars, and we'll be trying to pull in some data from there as well, right? So just to give you an idea, these were some of my mentors. The first one was Dr. Yannick Delil. Yannick Delil was part of the Planet Sciences. It's an organization that helps with researchers and astronomers with these kind of observational sciences. So it was through him that I could work on the observatory project. And we have Dr. Dirk Frobreek. So Dr. Frobreek is an industrial advisor who is a part-time astronomer as well. So he has written a lot of articles and research materials, and he is also a director of a sister observatory that we were working on called the Beacon Observatory. And Dr. Jaroslav Mek is again an industrial advisor. So he's an astrophysicist by profession, and he has done his postdoctoral at Charles University Prague, which is also a university in France. And so these were the three advisors and mentors for me for three different projects. Yeah. So we get into our first project that's called the Exoclock project. So it deals with the study of exoplanets, where we take several pictures of the transit that is happening of the exoplanets across a variable star. And we look at the dim spots and the bright spots, and based on the magnitude and time of it passing, we'll try to plot a light curve, and we'll try to do further research on it. Now, before we move on to our major project discussion, I have conducted a sort of a little literature review for my project requirement, based on three major books and journals, majorly written by
ওখানে
my mentors,
এখানে
as
কিছু
well
করতে
as
পারবো না
some
এখানে কিছু
other
করতে পারবো না ওখানে
astronomers.
কিছু লেখা থাকলে
Now,
বলো
from the
বলতে
mentioned books, I have got some, some strengths and drawbacks and some scopes of improvement as such. So, some of the strengths, as you can see, is,
বলো 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 বলো
it explains some basic practical approach, which makes it easier for us to,
মাইনাস না প্লাস আছে
collect some pristine data. And,
উইথড্র
as amateur astronomers at the time, it was really easy for us to, understand what is happening and
ক্রেডিট মানে
really
জমা
get a complete picture of, how to go forward with these projects. So that is why I'm suggesting these projects for you,
উইথড্র
because
ডিপোজিট অ্যাকসেসটা
these are
দিয়ে
not a
দিয়েছে ঠিক
very
করে
high
লিখে
level
দিয়েছে
projects, but are also at the same time carries a lot of weight in itself.
ও
So you
ওই
will
যে
be able
ব্র্যাকেটে
to
লেখা আছে না
understand
ডিআর
various,
সিআর
phenomenons, as
এই
well
যে
as
এই যে
understand
ডিআর
the
লেখা
scope
আছে
of
না
the project, while at
ডিআর
the
মানে
same
ডেবিট
time you can
আর
improve
সিআর মানে
as an
ক্রেডিট
amateur astronomer as well. And it demonstrates various techniques to optimize data procurement and processing, and provide some scientific background to the kind of insight you require for data
ডেবিট
analysis.
মানে কাটা
And and most importantly, they are, they deal, or they are the base for a lot of dynamics that is happening on a
হুম
solar and planetary basis. So
কোথায় লেখা আছে
it
দেখো
might look simple from the outside. I mean, it is quite simple to understand and to execute,
হবে হয়তো
but the scope of these kind of projects would be very,
একটু
very
ব্যস্ত আছি
impactful when it comes to, the space agencies and
পাশে
the
কি
observational
কি লেখা
sciences
আছে
that you're
পাশে
dealing with. Now,
দেখি
some of the
তাহলে
drawbacks
এইটটি
would
বেশি
be, yeah. So lack of
ব্যালেন্স
equipments can be a
এখানে
drawback
কি লেখা
when,
আছে ব্যালেন্স
if you're
কিছু
not
লেখা
working in an
ওখানে পড়ে
observatory,
আছে
or
আসার পর
if you're not working in the exact observational sciences setup, which I had discussed in the previous sessions. I had discussed in detail about the kind of setup that you require. So
পরে আলোচনা করছি
in
ওকে
the setups, you will require various, dimensions of a telescope, and various camera settings, temperature requirements, filter requirements, light setups in your dome or telescopic dome, etc. So if that is not sufficient in our environment, then that could lead to some lack of precision data. But again, these days we have a lot of, what do you say? We have a lot of technological advancements with various softwares and tools to help you make your data as precise as possible. And some proposed approaches may retain some, constraints, and some momentous constraints, wherein you will have to, neglect some factors, and try to go around it with various other constants that you have. And some of the scopes of improvements that I personally felt after going through the materials available to me, that is that we can improve a lot by providing some accessibility to sensitive data, which I believe in the close future we should be able to. And so if these sensitive data are available to us, we should be able to go a lot more into the efficient, conclusive data procurement. And even some data error dilution can be adopted. Like, we do deal with a lot of trial and error methods in this. We have some error bars, error marks. All these could mean a lot to your final uh, conclusion. And again, some general enlightenment about exoplanetary studies can be increased in a general note. So that is why we have come up with certain workshops and project scopes for even the students who have not gotten into the astronomical background, wherein they would be able to understand at least, if I tell you the term exoplanet, you know what an exoplanet could be. So again, those of you who are not able to follow what exoplanets are, we do have previous sessions exclusively done for exoplanets. So please do check them out and get a general idea about what exoplanets are, what planets in general are, and how different exoplanets could be from planets based on the properties, or based on the appearance, or based on the surroundings of it, the orbits, etc. Right? So that is about the literature review. So moving on, we move to the methodology part of our project, and we can broadly divide the steps of methodology into obtention, analysis, and interpretation. So these are the three major divisions that we have for any methodology that you take. You need to obtain your data, analyze your data, and interpret your data. So that is broadly anything, any field you work in, your methodology of whatever data you're dealing with could be these three. You obtain it, you analyze it, and you interpret it. So it is based on these three steps that you finally arrive at some conclusions which will help you for your further research or analysis, etc. Right? So your obtention in our case was done based on several photographs that we took in the observatory using the telescopic setup of the exoplanet transit in front of a star. And we analyzed it using certain softwares, as well as with visual detection. And some stars appear fainter during transit, and during the transit, whatever faintness or the brightness that you see will be plotted down into a graph. And so that this variation of light is measured using a light curve plot. And we have already discussed about light curve plots and how to analyze them, or how they are plotted. And how you interpret it is, you again use some tools, softwares, to carry out some careful analysis, and even some manual calculations can be made to pull in some, some data, like to calculate densities or radius or volume, etc., using some very known formulas that we have already learned through high school or college. Right? Now, again, so once we have crossed, once we know the broad, differentiation between these three steps, we get into the detailed steps. Okay. So the first step is your target selection. Again, these six steps we have already discussed in previous sessions. I'm just brushing them through so that we don't lose the kind of connection we have from the previous session. Now, the first one, target selections. So we select our targets based on various factors, like the sky, the coordinates of the place that we observe from, and mainly we try to focus on a place which has an absence or at least minimal light pollution, because light interference can cause a lot of differences to our observation. Light interferences can bend our observations in such a way that we can have some apparent light falls, and we may see something that's not there, if you put it in, if you put it bluntly. So absence of light and absence of any sort of light pollution or interference is extremely important for any kind of observations. Right. And the second one is observational setup. So we usually require a CCD camera, which is charge coupled device camera. Now, the thing with CCD camera is, on one hand, it is really expensive. So we find those kind of cameras only mostly, not only, but mostly in the kind of observatory setups. And these cameras require some very close attention and care.
Goodreads.
So they are very
Goodreads company.
sensitive. They have very sensitive elements in these kind of cameras. So you need to keep it down to a temperature of around minus 30 degrees Celsius. So it has to be really, taken care of to make sure that you get the right kind of data procurement. And also we used for these projects, at least we used a specific telescope called TJMS telescope. It has a telescopic view of 600 mm and a focal length of 2 meters. Yeah. And next one is data acquisition. So we can acquire data by manually setting up your telescope and trying to gather as many images as possible in a given amount of time. But to make this easier as well, we have used a bunch of other softwares to cross check and see if we are getting the accurate data. So again, we've used another online database which we've been discussing in the last couple of sessions called AFSO to acquire the basic data like variable star plotting to begin our session with. So variable star plotting will help you to understand that, what are the other kinds of stars, comparison stars that is available for you for the star that you're trying to observe. So based on similar magnitude, you may be able to choose another neighboring star, so you can compare with it and you can refer it throughout your study about your current star. So in any kind of observations that you see in astronomy, it is very important that you have a reference something. So you will have a reference star, or you will have any sort of reference body to see how the changes happen in your target with respect to what your reference is. For example, for exoplanets, it's a reference host star. So since exoplanet is a celestial body that does not give out light, right? So it's not a star. So any planet or planetary objects does not give out light of its own. So it is a solid body with no emission of light from it. So you take a star, a host star around which this exoplanet could be revolving, and you see how the light is being covered when this particular exoplanet is moving in front of the star. So based on, if you know the host star's light capacity in an original way, and you see how much of that light is being covered by the exoplanet when it moves in front of it or when it transits in front of the star, you will be able to say that what could be the magnitude, or what could be the volume, or what could be the various factors or properties of this exoplanet is. Right. So that is the main way of understanding through transit photometry. And it's also the importance of having a reference star always when you observe.
मोबाइल नंबर
So in
कंप्लीट
this
हो गया
AFSO, again,
कंप्लीट
we enter the coordinates of our place of observation, and we get
टीपी
the
ने
star
और नहीं है
chart,
ना
and we process the
बोलिए
data that we get along with the transit images that we procured through a telescope at different times throughout the duration of the transit. And we have these images that we have procured in three different basic
मोबाइल नंबर
filters. So these filters are RGB filters. We have red filters, blue filters, and green filters, which is called visual filter, direct filter, and infrared filter. Right. So, and from these three filters, you will be having the raw images in these filters. You try to reduce them, and we make it to sets of 9 images each. And we'll have 3 three out of these 9 images, we'll have three images of reduced format for red filter, 3 images reduced format of green filter, 3 images reduced format of blue filter. And we also have reduction frames. If you all remember what reduction frames are, I think our old students who had already attended previous sessions, Likit, Praful, Saumali, any of you want to tell me about what reduction frames are, if you remember?
Blue filter, red filter, madam.
Sorry, reduction frames are?
Uh, blue filter and red frequency filter. I think.
No, those are the color filters. Reduction frames would be something else.
Ma'am, that something like correction images that is used during some data reductions.
Exactly. So reduction frames are nothing but I had given an example back then, like when you have kept your eyes closed for a long time, let's say you're sleeping. When you're sleeping and you wake up suddenly, and if someone switches on the light, you will find it very difficult for your eyes to get adjusted to the kind of light that's coming through, right? So that is exactly what we are trying to change for a telescope also, or for a CCD camera, or since the camera we are using a CCD and they have extremely sensitive lenses and extremely sensitive parts to it, they suddenly when you observe something through a telescope, the light coming through that would be pretty heavy on the camera lens since it is very sensitive. So to get it to adapt to these kind of lights, what we do is we try to give a plain white filter, a plain white frame. Like for example, on telescope, if you're working live on it, you just put a white cloth over the observing lens, and you try to capture an image of that. So the white cloth will give some sort of white bright light sort of effect to the camera. Then you immediately put a black cloth and try to capture that. So you do this 3 times. You will be able to reduce a lot of grainy effects, and you will be able to reduce a lot of any static noises, any noises that comes in when you try to capture something. Noises are nothing but some disturbances in your image. So all these can be removed by just making your camera lenses more adapted to the kind of light that is going to come into it, right? So if you're all set for your event, so we usually capture images for a certain event when it happens, right, in the outer space. And if you're completely ready for your event, and if you start capturing, and if the camera lens is not able to accept that kind of light that is coming all together into the lens, you may not be able to capture it in the most precise way. So beforehand, you try to prepare your camera lens for the kind of light that is going to come into it. So that is what is reduction frame called. And we have 3 kinds of reduction frames called bias frames, dark frames, and flat frames. And we use 5 of each. We use 5 bias frame, 5 dark frames, and 5 flat frames. Each of these frames are white, black, and no color intended. So these each will support in some removing statics, removing noises, to increase your focal length, increase your focus power, and to remove any kind of noises, basically. So these are called the reduction frames. And your fourth step is transit modeling. And your transit modeling again has your few steps in that, like image reduction, image alignment, photometry, transit modeling analysis, So all these were also discussed in our previous sessions when we went through each of these topics in detail. Now, these steps are done, the transit modeling steps are done using some 24 images that we have saved from the previous, data acquisition, wherein we have sets of 9 images of 3 of each filter, then five bias, 5 dark, 5 flat reduction frames. So all of these together, you will have around 24 images, and we work the rest of the steps with these 24 images. Now, from something you need to learn, understand from here is in your first, or let's say your third steps beginning, when you start taking images of your event. I have mentioned this. If your event lasts for 4 hours, let's say, okay, let's say a transit is happening, a planet transit is happening for 4 hours, or if a sort of an eclipse is happening for 4 hours. So if it is happening for 4 hours, you you start your recording, you start capturing your images right from 2 hours before the event happening and 2 hours after your event happening. So that's a total of 8 hours. So for a 4 hour long event, you should have 8 hours worth of images captured. And you can set up your telescope to an automatic, what do you say, automatic capture of at every 2 seconds or every 2 minutes. You can set it up however you want. Now, in between, you will have to just change the focus because the sky is constantly moving. So after a while, after a few minutes, you may observe that your focus that was set in the beginning of the observation may not be the same because the sky is constantly moving in the east-west direction. So you need to have your focus realigned every few minutes. So that is the only, when we are observing, that's the part wherein we have to be careful about. So imagine for an 8 hour long capture, you set up your camera to capture an image every maybe 2 minutes. How many images can you have? You can have like thousands of images, right? You can have 1,000 images, or there are some events, some overnight events wherein I think the transit was happening for around 9 hours or so. So right from sunset, we were awake till the sunrise in the morning, and 2 hours before and 2 hours after that gives us roughly around 12 hours of observation. So you don't really sleep for 12 hours. So we just survive on a lot of coffee and a lot of taking shifts to go change the focus, etc. So that is where we have to be careful about. And those kind of events, we could be gathering at least 8,000, 9,000 images. Now, these would be raw images, and we will be constantly, um, capturing these. And at the end, from raw images of some 8,000, 9,000 worth of content, you will be reducing those images down to 24 images. Now, that is a crucial part because you will have to see how much of noise is involved in each of these images, and you will have to reduce accordingly. So, yeah, so that is one thing that, that's one thing I wanted to let you all know here. So by the time you have reached your transit modeling, you have 24 images at hand, and we use softwares like Munivin or Hops. So Munivin and Hops are ESA approved softwares that is used in their European Space Agency for various exoplanetary as well as star-based transit analysis and modeling. So HOPS is nothing but Holloman photometry software. So it is a photometry software where you conduct all the photometries and preliminary spectrometries as well. So from there, you go to software analysis of the data. Now, that is primarily about the data analysis that you do during using these softwares called Munivin or HOPS, in which we do photometry and some reduction to process the pixel files that we have achieved. Now, this is done by focusing the analysis on the reference star, as I've mentioned earlier. The reference star will have some inner and outer radius of aperture, and we'll be comparing with those apertures of the known stars so that you can try and compare and come to some conclusions or some assumptions at least about the target that you're trying to observe. So again, about apertures, inner sky, outer sky, aperture radiuses, I've shown you with images in the previous sessions. So for those of you all who are not able to follow here, please make sure you go back and check the recordings from before. And anyway, so once the software analysis is done, you get a light curve that is generated. Now, light curve is just based on time versus magnitude graph, and this light curve is uploaded into an exoclock database. So exoclock project that um, I've I've been talking about this project uh, is an approved project, a government approved project, wherein whatever observations or whatever light curves that you have generated using the images that you have procured, you will be uploading that light curve plot into the European Space Agency's portal. So at any point of time, let's say 200 years from now or 100 years from now, even when astronomers at that time try to check and get some data on some particular star, they will be getting the light curve that is generated and uploaded by you. So even in our project also, there were scenarios when we were referring to light curve plotting that was observed back in the 70s. So back then there was no website of this sort, so they were manually recording it. And later, when the website came into existence, they uploaded all the old data. So even the observations from that year or from the 60s and 70s could still be available to us, including the observer's name and all that. So it feels special to have your name on that kind of a space agency's website. And yeah, so we'll be uploading into this database called exoclock, and some other observations that we have gotten on the way of this project also will be uploaded there, so that anyone at any point wants to refer these, they can do that. And this data will be later referred to by some all the space agencies, although this is under European Space Agencies. Even European Space Agency or NASA, or even Indian space agencies or Indian space organizations will be referring this for any kind of further studies on exoplanets. So that is about the software analysis of the data. Now, so the result generation is nothing but whatever data, whatever conclusions you are able to draw or derive from the kind of data that you have absorbed throughout the project. And you will be able to understand a lot about the factors or properties of these kind of exoplanets, and you can name them based on the star that you have seen it revolving around, and you can just upload it simply. Now, taking you through some little glimpses on the exoclock project. uh, this was the project setup. So this is the dome part of the observatory. So this is where you can manually set up your telescope if you want to and see the sky up high. And this is our telescopic setup. And this dome that you see that is going around is the outside view is this one. And this was my team. So we had published our first light curve plotting, and when the publish was accepted by European Space Agency, that was a joy we had. And yeah, so these are our observatory moments, and these are with my mentors. So if you're all interested, there are various opportunities in observatories around the world, in India as well. So if you ever get a chance, you can also be part of a lot of projects like these, wherein they really require some people to help them with some project details and some um, project conclusions and all that. and procurement and analysis. So this was when we had published HAT P20b is the exoplanet that we were observing. So HAT P20b is the name of the exoplanet, and HAT P20 is the star that this exoplanet was revolving around. So HAT P20 is the name of the star, so we named the exoplanet as HAT P20b. And we had put in the light curve. We had observed this particular exoplanet, and once all the data acquisition was done and processing was done, we did the light curve, and we uploaded to exoclock database. So even now, if you go to exoclock database, you will be able to find the light curve of this particular exoplanet uh, under the team's name. And yeah, so these were just to give you a few glimpses. Yeah, so these were the two exoplanets that we had observed, and these were the outcomes. So ideally, if you check, this is the ideal sort of data that you need to have. Okay, so we have light versus time. Now we have a planet, exoplanet, and there is a host star. Okay, so when this planet is outside, okay, let's on a 2D plane, if this planet is coming and till it touches this particular border, right? Till it touches the border of the star, the light of the star is entirely given out. So your light should be at this point of time, your light should be somewhere on the maximum of the star. Okay, then the planet crosses across the star. Now, let's say when the planet sort of enters the border, it slightly starts dipping down. Okay, because the light from the star is reducing because there is a covering happening. It's like an eclipse. Okay, the light is reducing. When it's in the middle, it's the least because that much of a light, this whole black area of light is being covered uh, of the star, right? So there is a maximum dip here. Then again, once it is going across and leaving the border, it'll again come back and the star will completely have its old light again. So an ideal light curve of an exoplanet should look like this. Okay, there is so yeah, so the transit event that I was talking about is the time from touching this border of the star, the exoplanet touching this border of the star, to the time it leaves at this border of the star, right? So this is called the event. Now, if this event takes around 4 hours, it's very important that you start observing from 2 hours before that and 2 hours after that. Only then, the importance of that observation is that if you don't have the 2 hours, let's say 2 hours before and 2 hours after, you will be only getting this dip, right? Now, only if you have 2 hours before that, you will be able to see what is the actual maximum light
आपका बिल नहीं
given
चाहिए
out by the star.
आपका बिल नहीं
So,
चाहिए
so then you can compare it both the
स्कैम
ways.
नहीं
You can
चाहिए
compare it before and
स्कैम नहीं
after, and you
चाहिए
can see the clear dip that is happening
आपका
in
बिल में
between.
स्कैम नहीं चाहिए
Now, this is an ideal light curve formation. Now, in case of
आपका
HAT
बिल नहीं
P20b,
चाहिए
this was the kind of dip we got. Okay, the predicted start was here, the predicted end was here, and we had we had observed this, and this was the light curve generated. And any residual errors were recorded this way, right? So all these dots that you see are various observational records that we had. So all these observational records give you some scattered data, and then you take the mean of it. So you can see here the mean is collected and drawn. And yeah, so some analysis done were here. Same we did again for another data called WASP-84b. So there were two exoplanets that we observed back to back in a span of, I think, around 10 days. And yeah, so WASP-84b, again, when you do an observation, there are a lot of things that can go wrong. So one day when you set up for an observation, your sky can change, your a lot of things can change. So all of these observations are not taken at the first time this transit happens. So we wait for it. Some days it goes wrong, some days halfway through we might lose a few data, or the sky begins to become weird. So all of these happen, so we'll have to call off the observation somewhere in between. So after repeated tryings, a lot of sleepless nights, this is where we finally could get into an observation of these exoplanets. So again, VASP-84b, again, it had a very gradual data, and our first 2 hours was very clouded. So our images were not straight up needed, but we got this curve. We got this curve, so you can imagine it's going somewhere here. And at least we got 1.00, which is an ideal way of checking your flux. So yeah, so this was taken into consideration, and we got the dip, and we got all the subsequent data based on this. Yeah, so this is just about how this was uploaded into the exoclock database, and even later you will be able to track on whatever agencies have visited your light curve data, and what have they used it for. Because whenever you try to get a data from this exoclock database, you will have to state the reason of why you're using it, or what kind of project are you going to do with it. So as the owners, or as the observers or astronomers who have uploaded these data, it is available to us, where we can see who all has observed it, and for what all projects they've used it. So that is about one of the projects. So hope you got a clear idea about what this exoclock project was. Coming to our second project, right? So our second project was called the HOIS, or the hunting of outbursting young stars, um, where I was surveying some nearby young stellar clusters they had available on the night sky at that time, the winter sky especially. So winter skies are kind of a little difficult to observe, because you don't have a clear sky all the time. Winter skies can be slightly more clouded than the summer sky. So here I had looked through some young stellar clusters and some star formation regions that is visible from the northern sky that was in at the time, to study about some variable young stars. So again, a few literature reviews were conducted, and this was especially based on the articles that was written by my mentor, especially Dr. Frobre. And so some strengths again when it came to outbursting young stars. So previously we had discussed about our exoplanets. So that is a different approach, because exoplanet in itself doesn't have a light of their own. You always observe it based on the star that it surrounds, revolves around. Now, observing an outbursting star, outbursting young star, the name itself, you may be able to understand that it is a star which has just crossed its birth phase, and it is a young star. It has not lived a lot, and there are certain outbursts that is happening within the star, and these outbursts are what we are trying to observe. Okay, these outbursts that is happening within the star, we try to observe, find data, try to draw some conclusions out of it, is what the whole project is about. Now, this one advantage of HOIS Citizen Science Project is this is completely done remotely and online. Okay, the scope is completely remote and online. Now, this is one of the projects that I would highly recommend to any of you who wants to go further on this line of field. HOIS, or Citizen Science Projects, holds a great weight and value to the projects, and it is completely be done using a laptop. Now, for HOIS especially, you don't have to procure your images on a live basis. You have tools wherein you can request for them to observe, collect images, and give you. Now, all you have to do will be, once you get this raw image file as a zipped file, you will have to reduce it, go through a bunch of steps, generate a light plot and light curve plot, and try to draw some conclusions from it. Right. So this is one of the projects that I would highly recommend for any of you to try and explore and play with. Some of the strengths that I personally observed was it gives you a very clear picture about some stellar and planetary evolution, and especially some photometry and spectroscopy events. And it gives you a really immense exposure and learning phase over some collaborative data procurement, because what you will be working on this citizen science project on an online platform, you will be able to connect with a lot of people who are working on the same project as you are. You can share information, you can share knowledge, and you can all collectively whatever you've worked on the citizen science project, you can later publish as an article or a research content. And it is very it's a big learning curve you have through these kind of projects. And you can always go for some unexplored young stars, because there are thousands and millions out there where you can really just plot down some stellar properties. And it's not as difficult also, because a lot of stars are untouched based on their properties, and these untouched stars may have a lot of familiar qualities, familiar properties. So you just have to get a reference star, find the properties, try to plot them against each other, see what are the stuffs that is not going together, what are going together, so what are the conclusions that you can draw from it, and just put it on a paper and publish it. So this is your Hoist citizen science project. Some drawbacks were that it kind of conceals climatic scientific data. Now, that is not coming into a lot of consideration here, because you don't have to go for any climatic based scientific data, because a software would be observing on your behalf. And again, precision equipments, all the precision equipments, or any sort of induced inferior raw data, all these would be a challenge when you have to observe on your own. But since we have softwares to do that work for you, and tools to do that work for you, pretty much negligible drawbacks we have. And yeah, there are a lot of scopes of improvement, because there are a lot of untouched stars as opposed to exoplanets, wherein our resources are less. When it comes to young outbursting stars or young stars in general, you have a lot of stars to observe and draw data on it. Again, your methodology part of it. So we begin as usual with the target selection from Hoist database, and based on factors like the season. Since I was in the winter season, I chose my winter season sky accordingly and my northern sky. And for this project specifically, I worked on M42 Orion Nebula. So that was an open cluster that was available for my sky at that time. It is in the Orion Nebula, and it is called M42. So it is one part of the nebula, and that was the young outbursting star that I chose. And once we choose or lock our target, I
আচ্ছা
can
মোটামুটি হয়ে
request for
যাবে,
the approval of my
বাট রাত্রেটাই
submission
খাবার।
on a portal that I had previously introduced to you all, called LCO portal. And within around 5 days, they will give you all the it'll analyze your submission and complete the data acquisition. So they will basically do the work of telescopic data collection for you. So they will have a team that is setting up the telescope and doing the observation and collecting all the images upon your request on behalf of you. Right, so you will get all the accurate images that you need, and you will be able to get all the data acquisition. So once they have approved your submission of your request, they will start doing the transit. And in the same portal, you will be able to see if you're confused about what target to choose, or what kind of
বালচোদার সিগনেচারটা
Please give me a moment. I'm sorry. I'm just, I am required to take a screenshot of this session. So I'm just on it. Okay, cool. Yeah. So again, yes, as I was telling, the team that is working elsewhere will do all the work for you, and you just have to give a request. Once they approve your request, they will start the work. And if you're confused about what kind of target to choose, or I don't know anything about these kind of stars, they will give you a list of events that is happening in the upcoming nights. So you can book for something only for 7 days at least from the date of your booking, so that they can prepare and everything. So that is also a work I had undertaken in the observatory that I was working in. So even that observatory were undertaking works like these. People who put in requests through the HOIS or LCO portal, we were getting that data. We were getting those requests, and we used to observe on their behalf and submit those images back to them as well. So that was also one. So that is how I got to know about such a portal, and I tried myself to do a project through that portal, and it worked. So yes, they will give you the upcoming events that is going to happen in the sky in a span of at least 7 days later. So you will be able to choose one of those targets, and ask them, request them to please take an observation of this event for me. And they will give you all the images, all the raw images to you, and you will have to reduce it, process it, and do the rest of the steps as it goes. And so you will get to know about the telescope that is used. In my case, in my project, they had used a telescope of 0.4 meters, and it captured around taking 9 exposures of one single target. And that event I had chosen is of 21 minutes and 58 seconds, so around 22 minutes. And they give you all the instrument configurations, all the exposure time, the filters they use. So the exposure time that they had taken was in 21 minutes and 58 seconds. They had captured one image every 120 seconds. So it's counted in seconds. So basically, every 2 minutes they captured an image. So I got around 10 raw images, and by default I think by default every 7 seconds there would be an image captured as well. So you will get those 10 main images, as well as the all the images that comes from every 7 seconds. So you will have like a collection of 200, 300 images, wherein you have to just filter through and run it to reduce it, and add your filters and your reduction frames, and you're good to go. So I had to basically choose my target, considering if my target is under 45 degrees of the horizon, otherwise the telescope will not capture it to take observation. So all of these can be easily done on the portal itself. It will tell you how much degree inclination is that this particular target is, how much degree inclination, and if this is possible by the team, or if you have any other options. All of these will be done by the tool called LCO portal. Now, once I got my images and some characteristic report, which they took around 5 days to send me, I moved on to making some color images. And these color images are to understand the various temperature variations happening. In the upcoming slides, I'll show you those colored images as well. And I tried using some softwares called JS9, DS9 softwares, although DS9 was more user friendly. So in DS9, we sort of filter the gray monochromatic images, because any image that you get from them are all monochromatic images. And these monochromatic images will be taken into consideration that is captured by the telescope, and you add three different filters, RGB filters, onto it. And it is interesting to note that very blue images, that is some white dwarfs or faint, or it's extremely hot, and some red images are red supergiant. So I will show you those in the upcoming um, images. Then, as I told, we'll add filters, reduction frames, etc. Now, this image, whatever you have tried to color grade, that will be later stacked into a Python programming, and that is done through a launch binder called Jupyter NB platform. And then later you process the images, and study the color changes and identification, light curve analysis, etc. So, to give you a quick look, my first part of my LCO portal will give me a list like this, saying these are the clusters on your current sky, because this was my winter target. And these are the clusters on your current sky. It is at a right ascension of this much, and your declination is this much. So, based on the declination, you can choose what kind of nebula you want to be looking into. So, for me, these three nebulas were most easily available. So I chose the Orion Nebula because that is what I'm more familiar with. So I chose the number 3 that you see here, M42 of Orion Nebula. Later, I submitted my request asking if they can, please do the observation for me. And once it was submitted, they have completed. Once it was, so you can keep checking your update, right? Sometimes you will see it is ongoing, and sometimes you will see it's been completed by them. So once it's completed, you will be able to find your API file here. You can simply download it, and you can get duration of this much seconds and instrument used, and you will get all the images that they've captured, right? And once that is done, um, I have run it on a DS9 software on which I could color grade it, and I've color graded it to an RGB profile. And certain things, if I had the original images of these, you would understand certain dots that you see in the red ones may not be repeated in the green ones, or it may be repeated on a different note. It may be fainter, it may be brighter. So you can see that however this filter is going through. So what is the main idea of using RGB filter? The main idea of using RGB filter would be to see how that particular color, like for example, if you're using a red filter, right? A red filter would close down or block all the red colors, that is red wavelength that is coming, and will show project the rest of it. A green filter would block all the green filter coming, and it will show the rest of it. Blue would do the same. So this will help you analyze what colors can fall into what. And basically, once you have, once you have superimposed all three images, you will get something of this sort. So this is what I have observed through my telescope. And this is the final image that I have superimposed and got. And this image, if you see certain points, like in this image, for example, in this particular star that you see, or
स्टेम
this
डाल दिया
particular little cluster or
स्टेम डाल दीजिए
star that you see, there is some
उनको पूछिए कहाँ
red
डालना है
color
बोल देगा कहाँ
border on
स्टेम
this
डालना है
side.
एक बार बोल
There
दीजिए मैं
is
थोड़ा
some
बिजी
blue
हूँ
color border on this side, and there is white space in between. So white
स्टेम डाला
space
हुआ है
is
ना
nothing but the
उधर ही स्टेम
proper
डालिए
superimposition of RGB colors. When red, blue, and
ठीक है
green
दीजिए दीजिए
filters
दीजिए
coincide with each other, okay? When they are superimposed one on top of the other, it will give you a clean white spot, right? So this image is blocking all the wavelengths away, and this is the brightest of the star that you can see. Okay. Now, any other places that you can see a little red tint, blue tint, there you can understand that the temperature variations are very high. Now, as I've told you, red color is associated with cold, and blue color is associated with hot. So red color, anything you see red color are all red giants or red supergiants. all that you see here. Anything you see blue, I think there should be a few blue dots that you see. Yeah, there is a blue dot here, this blue dot here. Yeah, so all these blue dots are very faint because they are white dwarfs. Okay, they are extremely small in size. I'm sure you can see a blue dot here, blue dot here. So all these are extremely small and faint. So they are extremely hot as well because of the densities they hold. So yeah, so this is the final image that you will be able to procure. Sorry, give me a moment, please. Yeah. So the image that you will be procuring at the end. And later, what you can do, additionally, this was out of the project. I have just, I've done a little exploring of the software, and this is basically when where you can, you can just play with the software. You can see what are the various features of the software, and
Wait, mobile
in the
number.
software, you can, you'll be able to mark the visible and invisible stars on the sky. Now, from this
गाड़ी number.
image, you feel like there's a lot of black areas, okay, because the stars are not visible. But in fact, that is because of the light that is faint, the faintness of the star. But in fact, if you mark all the stars on that particular image, this is the kind of picture you get. And this sky will provide us a sort of a database on the characteristics of the stars, um, and various lines have been interpreted. Now here, if you see, if you see the uh, this particular thermal image that you see here, that has been interpreted as the brightest star of M42, the Orion cluster. That's called the Tech 01, Orion C. Tech 01 Orion C. This is just adopted just to see how bright it is and why the magnitude is the highest. So the highest magnitude that you can find for this particular nebula is 5.13, and this is the star that has it. So this is just a thermal image of that particular star. So these are some things that the software will do upon you just trying to explore through it. And we also observe that the stacked image here, these are the stacked images.
জুম করো,
Now, once the
জুম করে
images are
ক্যামেরা
stacked
একটা
like
ছবি
this,
তোলো তো,
you see this right hand image is a little more
এক্ষুনি
clarified
তোলো,
than the left images and has more
আমাকে দাও।
stars, visible stars, than the initial gray monochromatic superimposed image. So these are the various things you can do with the website and with the software, and you will be able to get a lot of data, a lot of learning from it. And even this particular screenshot that I've taken, it's a 3D simulation screenshot. So you can basically just, map through that entire surface and see what is high and what has what magnitude, etc. It's a fun thing to do, actually. And moving on, yeah, so this is just a sort of
ম্যাডাম,
to give you an idea. So
sorry ম্যাডাম, green color
yes.
for what reason?
Oh, the green color is just based on the wavelengths, right? So if you check the wavelength scale, your blue is the hottest and red is the coldest, right? So in that wavelength, if you check, green is somewhat in the
Okay.
middle, so you can consider them
Color
as
scale,
neutral.
temperature scale,
Sorry?
temperature scale, madam.
Yes. Temperature scale. This is just for our identification. In fact, the stars are not the stars are not of red or blue color, but we categorize them red or blue based on the wavelengths that we get from these sources, right? And these wavelengths will tell you about the temperature that these celestial bodies have. Got it?
Okay, madam.
Okay. So yeah, so these are the initial reduced images that I had from all the raw images that I got around 200, 300 images that I've got. I've tried to put it through, what do you say, various, biased images, biased and dark and various reduction frames, etc. And I passed it through a visual filter, which is blue, direct filter, which is green, and infrared filter, that is red. So this is just to give you an idea about the 3 filters that I've used, and the outcome was the superimposed image. Now, this image, these are the kind of images that is published in astrophotographies, and you have probably seen it in magazines or like on Google Images, and also these kind of images, if you're able to superimpose and get through these projects, these are what do you say, pretty Google image worthy kind of images. So yeah, um, coming to my final project, it is a long term project, so it will go on for a while. It kind of the preliminary phase just gotten over last year, so we have way more to go. And yeah, so this is about symbiotic binary stars, and we try to analyze the varying luminosity. And the project kind of the object of the project is to confirm how do you understand if a star is symbiotic by performing a photometry. So here, um, if you see like 2 stars, I mean, if you see one single star um, flickering, right? A flickering is a basic property of a star. Okay, you will sometimes appear like obviously we have all come from childhood listening to Twinkle Twinkle Little Star, right? So what is twinkle exactly? So the light that is going up and down, or the light that is becoming bright and suddenly faint, and then bright and then suddenly faint, so that is called the flickering of a light. Now, when you see a star flickering in the sky, is it because of the light apparition or the light variation on that star, or is it because of any other phenomenon? Now, the other phenomenon I'm talking about is the existence of symbiotic stars. Now, certain star groups, right? They exist in pairs. When they exist in pairs, what happens is these stars, due to the electromagnetic and due to the gravitational force, and also the centrifugal force between these stars, they keep spinning around each other. So what happens is when we are trying to observe from here, there's always one star that is coming in front of the other star because they are spinning, right? When 2 things are spinning in front of you, you see at a point of time, you see one star in front of the other star. At the next point, you see the other star in front of the other, of one star, right? So because of this constant flipping of positions, we tend to see a flickering as well, because for a brief moment, the light of one star is covered by the star in front of it, right? So this is the exact phenomenon we are trying to observe here, and we were trying to come up with identifying the flickering sensation using a sinusoidal curve, that is a sine curve, and we were trying to identify symbiotic stars. Okay. Again, the methodology is very similar to what we have discussed earlier, so I'm just going to very quickly brief through this. We have the target selection, that is using exospice.com, that I had introduced in a few sessions earlier. And the observational setup was done in an observatory called Observatoire de Sombéran. It is in the French Alps. And the data acquisition was done for 8 potential symbiotic stars that we were trying to focus on. And we used the software called HOPS for software analysis and light curve generation. And the final step, as this is very similar to the exoplanet or exoclock project that we have done. It's just a different location of observation, and a very similar process of following. Just at the end, when you instead of taking a light curve generation, we do a sinusoidal curve. That's all. So finally, for the last step, we determined if the found and analyzed star is flickering or not based on the curve that we got. And yeah, so some developments that you can see here are, I have, out of the eight symbiotic stars that we had observed, I have taken two specific here because we had the most varied data for these two. One is called the Sataha. This is pronounced Sataha. It's written STHA or STHA, but it's pronounced Sataha 185 and DTPSE. And yeah, so these two sinusoidal curves are, it is very similar to light curve generation, but it is slightly different when you enter the data, right? It is done almost mostly through the same softwares. Just the way of using is different because of the variation in data. So due to this sinusoidal curve, okay. Now the initially you understand this is a symbiotic star that is completely abiding by the way it should, because it has constant dips and creases. So this is because when one star is high, the other star is going down, the other star is high, the one star. So there is a lot of dips that is happening there. In DTPSC, you don't see a lot of dips, but despite that, it is still a symbiotic star. So we have conducted some researches and some articles based on that. So this was one of my articles that I had published on it. It's called Multi-Frequency Research of Symbiotic Binaries. Yeah. So certain outcomes that we were looking into, the minor goal was to identify the potential symbiotic stars, whether they are flickering or not, and whether they can be analyzed through light curve that is generated on the basis of sinusoidal curves. And the major goal was to work on some acquired data to publish. And this project was basically to present the work on a PROAM collaboration. PROAM is professional amateur collaboration of astronomers at SF2A conference in June 2023, which had passed. Anyway, so we are still in an ongoing part of this project wherein symbiotic stars, we are still going further on this project, and it is still an ongoing project. We are expecting to finish it, wind it up by 2026, which we started in 2022. So there are a lot of events that have to be captured, a lot of symbiotic stars that we are waiting to capture in the upcoming years and time. So with that, I conclude today's session. Anyway, thank you everyone for patiently staying for this long. Do we have any questions?
Madam, would you please tell again the process of data collection of the star? Recently, you mentioned
Sorry, I didn't understand.
the process of data collection of stars for project purpose.
Of data collection.
Yes, we have to give a request in a website, then they will give the details of the stars. You saying no?
Yes. So that will be the major project that we'll be discussing for your final project. So this,
Okay.
so in this session, I have just given you an idea about different projects that they have scope. You have scopes on,
Okay.
right? So we'll be discussing
Later.
in detail about how to request your how to request your data to this particular portal, and how they'll be giving you various informations about your data collection, etc. Yeah.
Okay.
So in another session, I'll share my screen and help you through that.
Okay, madam, no problem.
Okay.
Okay, madam. Thank you, madam.
Do we Yeah, no
Thank you.
problem. Do we have any more questions based on our today's session?
Mm,
No, ma'am.
Okay. So if we have any questions, please feel free to reach out. If not, we'll call it a day then. Was there anything in this session that you were not able to follow through, maybe because of the pace of my explanation or so? That was new to you, but you couldn't follow quite right?
Madam, you show one graph, no? The exoplanet
Yeah.
watch is there. Can you open that picture again?
Sure. Let me. Are you talking about this one?
This one. In this
Yes.
portion, the downside there is grainy curve. Uh, so can you little bit explain again this portion how you collect this data?
Sure. So, are you talking about this grain, this
Yes,
thing?
yes.
Yeah. So, I had mentioned about various, uh, observations that we'll be doing, right? In one single event, there will be a lot of number of observations that we'll be going through, right?
Yes.
So none of those observations will give you the most accurate or precise data because your focus of the telescope is constantly changing. It's like you're trying to balance yourself in the middle of a lot of wind, right? Storm. So it's that kind of a situation. So you have like a very strong um change in your focus. So in the middle of that, it is trying to give you observations or recordings of your various capture. So these captures will always be like, on an average. So it'll give you it'll give you a good capture here. It'll give you multiple captures through every point of this transit. Okay. Now, when you put all those captures or all those observations together, you should be able to achieve a sort of um, graph like this. Now, later, to give you a mean of this, we draw a mean line here and we check what is the depth of flux that is happening. Okay. Now,
Yes.
this difference in flux that is taking place is what will tell you how much of a light variation or light luminosity difference or light intensity difference would be happening during this transit. Now, that flux difference, right? This difference that you see, that difference will give you what could be the volume, density, radius, various factors about of this exoplanet. Now we'll be discussing about this also in detail about how to calculate what are the formulas used. You will be solving some live problems as well to understand this better. Okay.
Okay, madam. Actually, we are
Are you
collecting the light intensity of this planet in a zoom out form. Am I clear or not?
sorry? Can you please come again?
Ma'am, are you collecting this the light intensity with respect to time with a zoom out
Yes.
form of the planet?
Not a zoom out form of the planet. So what we do is when so one thing we can understand state at the beginning of this is the planet does not have any light of its own, right?
Yes.
Yeah.
Yes.
Only the star
Star,
in
sorry, star.
in this in this scenario, out of the planet and the star, only star has light, right?
Right. I'm sorry.
Yeah. The planet does not have a light of its own. So what happens is when the planet moves in front of the star, there is a covering of light happening, right?
Yes.
Yeah. So each of these, like, when you like, you keep clicking images of what this is, and from those observations that you have at every point of time, you will have multiple observations. And these observations are like, okay, So at this point, the light is more. Okay, the light is more, the light is more, light is more, light is more, light is more, the
Oh,
light is reducing, the light is reducing of the star. It is reducing and then it's coming back to normal. So this observation is done parallelly multiple times.
with respect to star and planet position, the lights come out from
Yes.
them. Reflection. We are collecting reflection result. With,
Not reflection exactly, it's more
intensity,
like
light
refraction.
intensity.
Yes.
I mean, I'm not pronouncing correctly, but we are collecting a light
No problem.
intensity of these events with respect to time.
That's exactly right.
Understand, madam. Thank you, madam.
Yeah. So these observations are done multiple times, and these multiple times are put together just to get a mean of it. Okay.
Okay, madam. Okay, understand.
All right.
Alright.
Okay. Yeah.
Thank you, madam.
So the similar thing is done in all these scenarios, and you have multiple observations that is put together, and you try to draw a mean of it. And you have multiple observations put here also, and you try to draw a mean of it. So yeah, that is about it. Do we have any other doubts, Rishiketabera?
No, madam. No, madam. Thank you.
No problem. And does any of you have any more questions to check with? Please feel free. All right, so if that's all we have, thank you, Ripple. Thank you for your confirmation. And if that's all we have for the day, we'll call it a day then.
Yes, ma'am.
Thank you so much, everyone. We'll see you again for the next session. So please stay tuned. We'll be discussing each of these projects in detail, and we'll have some problem solving during the session as well. So thank you, everyone. Looking forward to the next session. Thank you.
Thank you, madam. Good night.
Thank you. Bye bye.
Thank you, ma'am. Good night.
Good night. Thank you, Ripple.